Wonderful day, everyone. Welcome to Statistics class. For today's presentation, it is our Module 1, Topic 3, Summation Notation. To give us an encouragement before we start our proper lesson, let's be reminded by Proverbs 2 verse 6. It says, "For the Lord gives wisdom. From his mouth come knowledge and understanding." For today's topic, it might not be easy for some, but it's not impossible to learn something new, for God gives us a promise that He gives wisdom. Our topic is summation notation. So let's recall your basic mathematics and algebra. So this term is read as summation of xi, where I ranges from 1 to n. Again, summation of xi, where I ranges from 1 to n, is equal to x1 plus x2 plus ellipsis plus xn. Whenever you see this ellipsis, it represents as a series of numbers. If you can see here 1, 2, then the series of numbers would be 3, 4 until your n or your population size. Okay, what is this sigma? It's a Greek letter. Whenever you see in a formula, it symbolizes summation, or it is a summation symbol. And then I, located here, is our index. And then xi is our ith summand here in this term. And then 1 is our lower limit. And then n is our upper limit. So as you can see, we've started from 1, since it is our lower limit, until n as our upper limit. Again, you can read this as summation of xi, where I ranges from 1 to n. Example: X is the number of chapters in the 5 books of Moses, commonly called as Pentateuch, or the first 5 books of the Old Testament. We have the Genesis, Exodus, Leviticus, Numbers, and Deuteronomy. So our ith summand, or the xi, rather, the variable, we have the 50 chapters in the book of Genesis and the 40 chapters in the book of Exodus and 27 chapters in the book of Leviticus and 36 chapters in the book of Numbers and 34 chapters in the book of Deuteronomy. So let's compute for the following. So the expression is summation of xi, where I ranges from 1 to 5. That means our lower limit is from 1 and our upper limit is 5. So using the same term, xi, substitute the lower limit x1 plus x2 plus x3 plus x4 plus x5. So x1 is our 50. So 50 chapters, 40, x2, x3 is 27, x4 is 36, and x5 is 34. So when you will compute it or calculate it using your calculator or manually or your Excel, you can get a total of 87. If you got it, then that's great. Now, we have another example. Using the same example, but different expression, mathematical expressions. So here, summation of xi squared, where I ranges from 3 to 5. Take note of this. Our lower limit is 3 and our upper limit is 5. So using this same term, x3 as our lower limit squared plus x4 squared plus x5 squared. So here, the squared here is not the index, okay? It is the square. and I only here is our index. So 27, let's start here from 3 as our lower limit. 27 squared, 36 squared, 34 squared. So using your calculator or your computation, you can get 3,181. If you have got it, if computed yourself, then that's awesome. So let's review some theorems of one-way summation notation. So theorem 1, we have the theorem 1, the summation of the sum of two or more variables is the sum of their summations. Thus, summation of xi plus or minus yi plus or minus zi, close parentheses, where I ranges from 1 to n, and here is the sample size, is equal to, or the number of observations, summation of xi, where I ranges from 1 to n, plus or minus summation of yi, where I ranges from 1 to n, and plus or minus summation of zi, where I ranges from 1 to n. So let's prove it. So expanding the left side and regrouping, we have, so from the expression from here, let's say we're gonna use the addition, the plus sign. So summation of xi plus yi plus zi, where I ranges from 1 to n, is equal to, open parentheses, x1 plus y1 plus z1. So using the same expression, plus x2 plus y2 plus z2, close parentheses, again, plus using this series or ellipsis, meaning I have 1 here, 2, 3, until the upper limit of n. So plus xn plus yn plus zn. So just regrouping it, so it will not change the value even if you get the parentheses. So I can group here all the x, I will add it, so that would be summation of xi, where I ranges from 1 to n, and plus I will also group all the I variables or the y, so summation of yi, where I ranges from 1 to n, and then I will add all the summand for the z variable, so summation of zi, where I ranges from 1 to n. Okay, so another theorem 2. If c is a constant, then summation of c, remember this is a constant, xi, where I ranges from 1 to n, is equal to, you just factor the constant c multiplied to the summation of xi, where I ranges from 1 to n. So let's prove it. You know, the theorem must have a proof. So let's use here expanding the left side here, the left side, and factoring we get. So from here, so let's prove it that we can arrive until here to prove that this theorem is really true. So summation of cxi, where I ranges from 1 to n, is also equal to cxi plus cx2 plus ellipsis plus cxn. So since they have the same constant, so we can factor it out and then add all our summand. So xi plus x2 plus ellipsis until xn. So you can add this expression, these terms can be constant multiplied to the summation of xi, where I ranges from 1 to n. So let's have an example for that. Example, summation of 5xi, where I ranges from 1 to 3. Remember, our lower limit is 1 and our upper limit is 3. Using the same value that we have for the previous example, 5 is our constant. 50 plus 5 times 40 plus 5 times 27. So it is the chapters as well, using the same example in the previous slides. In the Genesis, Exodus, Leviticus, there are 27 in Leviticus. There are 27 chapters in the book of Leviticus. So if you add it, so 5 times 50, so same this, you will multiply. If you add it, it could be equal to 585. So what if using this the previous theorem, summation of 5xi, where I ranges from 1 to 3, so I will factor out the constant c, or the 5. So it can be summation of xi, where I ranges from 1 to 3. So I will add first here 50 plus 40 plus 27, and then multiplied, then they have the same answer. Okay? So that is the proof for our theorem 2. Now let's proceed to theorem 3. If c is a constant, then summation of c, where I ranges from 1 to n. So as you can see, there is no ith or ith index here. So you can have this term, this expression is equal to n, the upper limit, multiplied to your constant. So let's prove it. If in theorem, so all the xi are equal to 1, for example, then summation of c, where I ranges from 1 to n, then c plus c plus c plus c plus c until this is the n terms, it can be equal to n times c. For example, summation of 5. Here, our constant, or our letter C, is 5, where I ranges from 1 to 3, is equal to, here, n. Remember the previous theorem? It will be equal to nc. So, the upper limit multiplied to your constant. So, the upper limit, we have here 3, multiplied to our constant. C, constant is 5. So it will be equal to 15. So, or, using this same expression, we have summation of C, where I ranges from 1 to C. So, C plus C plus C plus C, since we have 3. Okay, the upper limit, so 3C. So, 5 plus 5 plus 5 is equal to 15. So, that's our proof for our theorem 3. So let's practice your skill. Okay. Evaluate the following notations using x1 is equal to 1, x2 is equal to 3, x3 is equal to 2, x4 is equal to 5, y1 is equal to 0, y2 is equal to 8, y3 is equal to 1, y4 is equal to 6. And z1 is equal to 4, z2 is equal to 7, c3 is equal to -2, and z4 is equal to 3. So, you have to compute for its sum with this given expression. For number 1, we have summation of 2xi plus yi, where I ranges from 1 to 4. And the number 2, we have summation of zi multiplied to yi minus zi, close parentheses, where I ranges from 1 to 4. And number 3, summation of xi plus zi, open close, squared. So you have to add it before you square it, and then where I ranges from 1 to 3. And then number 4, we have summation of xi plus yi squared, where I ranges from 1 to 4. And then summation of yi plus zi, where I ranges from 1 to 3. So using the value in this summand, or these variables, so you substitute it and use the principle for summation notation, and then as well as your basic mathematics or your algebra in computing for these numbers. So In your evaluation, what is your answer in number 1? What is your answer in number 2? What is your answer in number 3? What is your answer in number 4? What is your answer in number 5? If you've got this answer in number 1 as 37, number 2, 36, number 3, 125, and number 4 is 112, and number 5 is 18, then praise the Lord, you're awesome. Okay, before I proceed to two-way summation notation, I will encourage you again with our text. For the Lord gives wisdom. From his mouth come knowledge and understanding. Remember, the Lord will give you wisdom as we proceed to our topic. Two-way table. Okay, it looks scary, intimidating, but you can do it. It might not be easy, but it's not impossible to learn and master it. Okay, so using or applying the principle that we have in a one-way summation notation, we can also use it in our two-way summation notation. Whereas here, we have in the horizontal, or here is our category or treatments. Okay, and then in each treatment or category, this category could be gender, could be male, female here, can be religious affiliation, it can be your treatment levels, different fertilizers, different varieties, so different breeds. So you can use that as your category or treatments. So remember our basic concepts of variables. And then, in each category, we have the number of observations. In experimental research, they call it replications. Okay, so for example, in category or category 1, you have the 4 replications or 4 observations or 4 samples. So, okay, and then the number of units. So, Ni, so since it is a small letter, then I'm talking about the sample size, okay? So, 1 because it corresponds to category or treatment 1. So, whenever I say N2, what is the N2? So, you will say the number of units in the category or treatment 2. So, this is how you read this N1 and 2. Take note of the subscript because the subscript would represent or would signify the category or your treatments. And then here we can see here we are using the 2 subscript or with the 2 digits is 1 and 1. So what is this? So 1, the first digit represents the first category or treatment. And then the second is represents to the vertical or to the column, which is the number of observations. So they intersect here, or this is the intersection point. So y, would say the observations or the dependent variable or the outcome value here is y11. So that means it is the observed value from the category or treatment 1, observation 1. And also here, from the category or treatment 1, observation 2. So here, from the category 1, observations until your N1 because this would be the number of observations in category 1. So now, in also 2, in category 2, remember here, this is category. We have the number of P category. So you can have as many as you want. So let's say 2. So here, it is the observed value in the treatment 2, observation 1. Or this is also the observed value from the second observed value from the category 2. So here 2, 2. And so that's it. So the same principle until your P treatments. So I've already discussed this number of units so that it's symbolizes or signifies to the category 1. And then, what is this category total? Instead of saying or writing the category total, I can use this expression, summation of y1j. So it's a typo error. It is j, where j ranges from 1 to n1. So if I will write this way, I'm talking about the total of the treatment 1 because my upper limit is n1. Okay? And then, as you can observe, 1 here on the first digit is fixed, constant. So the one that varies or changing is here and the number of the observations number. So that means this is the category total of the category 1. Okay? So since the first digit or the 1 is fixed. Or you can also use the dot notation. If if it's hard for you or to save space and time, you can use also this dot notation. For example, y1 dot. That means it is the total of the treatment 1. So any or all observations from the treatment 1. So as you can see here, 1 is constant or fixed, and that is the one that varies. Okay, so that means it's 1, 2, 3, 4, so until your number of units in the corresponding treatment or category. So same thing here. Summation of y to j, where j ranges from 1 to n2. Remember here, the upper limit is n2 to symbolize or to signify that it is the sample size or the number of units in the category 2. So the same using the dot notation, y2, it's fixed and dot. So that means I have 1, 2, 3, 4, 5 until n2 observations. So here also you have the column. The same principle for that notation. However, the one that is fixed here is the column. Or here the first column or the first replications and a different treatment. So here all first observation or first replication of all category or treatment. So this is the total for that. And as well as the same principle that you can apply here. Summation of yi1. That means this first column or this first replication is fixed and where I ranges from 1 to p. So all observed value in your different categories, but only in this fixed replication or the first column. Okay, the same principle should be applied here. Summation of yi2, where I ranges from 1 to p. Okay, so same principle here, but as you can see here, this is the y double dot because it signifies it is called as grand total, meaning every observed value in your experiment, in all your categories, in all your treatments, that is the total. Okay, so it's easy to write this way, the dot notation, and then compare it to this because we can save time. Okay, so why should we learn this? Because whenever you know the principles or the concepts of this summation notation, even if you forget the formula, but if you know how to read formulas, you know how to read the concepts, it's easy for you to know the manual computation for a different statistical tool applying the principles of summation notation. So throughout our class, you will always use this summation notation with you so you better master its principle. Remember, this is the grand total. Okay, so to give you more background of it or to help you understand it more, here, Yij Here is the first index is I. It represents the category number, and then J is the number of observation in the ith category. So it is the jth observation. We say jth here, the number of observations of Y in the ith category. So where I ranges from 1 until P category or treatments, and J is equal to 1, 2, 3 until your sample number of units in that ith category. And then yi dot or equal to summation of yij, where j ranges from 1 to and j is the sum of values in the ith category. So here you can, this is located here, the total in your category. And then y dot j, j is fixed. So summation of yij, where I ranges from 1 to p, is the sum of values that belong to the jth observation. And also the y double dot is equal to double summation of yij, where j ranges from 1 to ni and I ranges from 1 to p treatments, or it is called as grand total. Okay, to give you an example, we have here the 4 categories and then the number of replications or observations in a different category. So our number of observations N1 in category 1, we have 3 because we have 1, 2, 3 observations. Okay, and then N2, in the category 2, number of units or sample size or number of observations, we have 4 because 1, 2, 3, 4. And then N3 is equal to 3 because we have 1, 2, 3 number of observations. And N4 is equal to 2 because we have only 8 and 2 number. And then there is only 2 observations. So what is this category total that we have mentioned? So as you can observe, 1 is fixed. That means in that first digit in the subscript, it is in the category 1. So it is equal to 15 because 3 plus 7 plus 5 is equal to 15. And then y2 dot is equal to 38 because 6 plus 9 plus 11 plus 12 is equal to 38. And also y3 dot is equal to 21. This is the category total in the third category. 2 plus 15 plus 4 equals 21. And then the category or the fourth category total is equal to 10 because 8 plus 2 is equal to 10. And then we have here the y dot 1. That means in the first column or in the first replication. Okay, so 3 plus 6 plus 2 equals plus 8 is equal to 19. So the same formula or the same principle that applies, you add here, and then we have the total number of observation, or this is our total number or subpopulation size. We have 2 plus 3 plus 4 plus 3 is equal to 12. So we have 12 number of observation in total in this experiment. And then the grand total is you have to add every observations here or the outcome value, and then it is equal to 84. So let's compute for the following. Double summation of yij, where j ranges from 1 to 2. Remember here, this is the column or the observations, and then where I ranges from 1 to 4, and this is the category, and then is equal to summation of yi1 plus yi2. So this will be our expression. And then because our observations is only in 1 and 2, so we only have 1 and 2, but the category varies because we have 1, 2 until our upper limit is 4. So to further express it this way, we have y 1, 1, because here I is we have to start in 1, then same here 1, and then 2, y11 plus y12, and then the second category here y21 plus y22, and then plus the third category, y31 plus y32, and then plus y41 plus y42. So we can see it here. So as expressed here in this term, we remember and take note, we only have 1 and 2 in this column, okay, with the 1 and 2. So here would be 3 plus 7, and then 6 plus 7, and then 2 plus 15, and then 8 plus 2 here is equal to 52. Another example using the same value. Double summation of yij squared. Remember, this is not the index, but rather it is squaring your value. So j is equal to 1 to ni, and then I equal to 1 to 4. So all 4 categories. So here, y1 1 squared plus y1 2 squared plus y3 squared plus y2 1 squared plus y2 2 squared plus y2 3 squared plus y2 4 squared plus y3 1 squared plus y3 2 squared plus y3 3 squared plus y4 1 squared plus y4 2 squared. As you can see, there is no 4 3 here. Just like here in this value, as remember, there are only, it is limited to the number of observations. So y4, category 4 is only 2 observations. That's why we have y4 1 squared plus y4 2 squared. So every observed value here, 3 squared plus 7 squared plus 5 squared plus 6 squared plus ellipses, that means until here, until 2 squared. So if you will calculate it manually or computer aided or using your calculator, you will get the value of 778. If you get it, then that's great. Then we also have theorems on double summation. Applying the same principle that we have in a one-way summation notation, we can also have these theorems. Number 1, double summation of yij, where j ranges from 1 to n1 and I ranges from 1 to p, is also equal to double summation of yij, where I ranges from 1 to p and j from 1 to ni. So what are the changes here? Even if you will alter change it, just like what we did in the previous example, they will just be equal. And also, we have double summation of yi multiplied to xij, where j ranges from 1 to ni, and I ranges from 1 to p, is also equal to grouping it according to their index, or summation of yi, where I ranges from 1 to p, multiplied to summation of xij, where j ranges from 1 to ni. And also here, in the third theorem, you can also have double summation of xij plus or minus the yij, where j ranges from 1 to ni, and I ranges from 1 to p, is also equal to, just like a distributive property. So double summation of xij, where j ranges from 1 to ni and I ranges from 1 to p, plus or minus the double summation of yij, where j ranges from 1 to ni and I ranges from 1 to p. Again, this is another theorem, the fourth theorem. But don't worry, you will not prove it. I'm just presenting it to you for you to be familiarized with it. Double summation of yi dot j, where j ranges from 1 to ni and I ranges from 1 to p, is also equal to double summation of ni multiplied to I dot, where I ranges from 1 to p. Remember our previous theorem in the first or in the one-way summation notation theorem. So the same principles. And then number 5 or fifth theorem, we have the double summation of c, where j ranges from 1 to ni and I ranges from 1 to p, is also equal to summation of ni c, or where I ranges from 1 to p, or it can be the total number of observations or the population size multiplied to your constant, where summation of ni, where I ranges from 1 to p, is equal to n. Remember that we have the n1, n2, n3, n4. If you will add it all, it will represent as your total sample size or the population size. That's why it's still letter N or the population size. So this is an example of proving. If you want to explore it, then try to prove or disprove this following expression. And also, using this one, you can familiarize with this, because in the later discussions or topics that we have, it is a formula that we will use in our computations. So you need to master it, because you need to use it in the next topic, especially in your readings with the formulas, how you do it, and so you have to master it. But you don't need to prove it. You just have to apply its principles. And also this one, the the deviation from the mean. So any deviation from the mean, the summation of the deviation of the mean will always be 0. It will be discussed later, but the same principles, it came from the double summation notation or two-way summation notation. So again, I would like to remind you the Proverbs 2 verse 6 that the Lord gives wisdom. It may be hard, but you'll be able to learn it. So continue to search things, and thank you. God bless you on the next module. Have a nice day.